Multivariable calculus, we are on section 14.6, day 2. If you look at the top, you can see two learning targets that I can write equations of tangent planes and normal lines. And in particular, we're going to make a new connection. I think more than a few kids might say, wow, we've done both of these things before. And you have, but you're going to see it in a new perspective. First of all, take a look at this directional derivative, so to speak. If you were to take the derivative in the opposite direction of a vector u, or a unit vector, the opposite direction, you can more or less see that the negative, because of the dot product, could come out in front, and it would just be the opposite of the directional derivative in the direction of vector u. Taking a look right here with our I, J, K unit vectors. I is the vector in the direction of the x-axis, positive x-axis, J in the positive y-axis, K in the positive z-axis. Of course, all of those are unit vectors with a length of 1. And I think you can quickly see what's happening. I would be 1, 0, 0. So this first directional derivative would be just the derivative of f with respect to x. Likewise, in the direction of j would be the derivative of f with respect to y. And then with z, the derivative of f in the k direction would just be f sub z. So any direction unit vector, and we need to change this right here, perpendicular or orthogonal to the gradient, is a zero rate of change in f, because, and you can look at this, and this might look a little odd at first. You can think, where's this cosine coming from? It's coming really from the fact that, this directional derivative can come from a dot product, and, of course, we've got the dot product's equivalent to be the length of vector A, the length of vector B multiplied together, multiplied by the cosine of the angle in between them. Remember, u is a unit vector. Its length is 1. So you'd have the length of the gradient vector multiplied to the cosine of pi over 2. Of course, that would be 0. So that hopefully can help you out. And of course, this is ultimately equivalent, like I was saying, to just the gradient dot producted to vector u. So yeah, as long as they're perpendicular, you'll have a 0 rate of change. So take a look right here. This is actually something really pulling some old material together too, even from our earlier chapters. Suppose that we do have a surface, and we have f of x, y, z is equal to k. In other words, it's a level surface of a function of 3 variables. Suppose there is a point x naught, y naught, z naught on that level surface, on that function, and it's on that surface. Let C be any curve that lies on that surface but passes through that point. Now, that C, you can see, is actually, I've highlighted in yellow here. And you might remember from chapter 13 that C can be defined as a continuous vector function. And that vector function is a function of t. So there is some t value that corresponds to the point. We could call that t naught. So since that curve lies on that surface, any point on that curve must satisfy the surface equation. In other words, it's satisfying the f of x, comma y, comma z equals k. So here's what we're about to do. We'd like to see if we could make some kind of a link with this surface in gray, that curve, and get a tangent plane as well. You can see in blue right over here, I've drawn a tangent plane. Well, you might wonder how that's all going to come together. Well, here's your f, and just want to real quickly draw off to the side that f, yes, is a function of x, y, and z, but because of that curve being defined with that continuous vector function, x, y, and z will all be dependent on that parameter t. They're functions of t. In other words, what we're about to do, guys, is we're going to take a derivative with respect to t, and we can come right back up here and do that. So as we take our derivative with respect to t, and that's why I made that little t diagram, that tree diagram. You can see what's going to happen. We'll have partial derivative of f with respect to x times a dx dt. We'd say plus, well, the partial derivative of f with respect to y times a dy dt. And then we'll say plus, well, what else? We've got the partial derivative of f with respect to z times dz dt. And of course, the derivative of the right side with respect to t, well, that's going to be 0. Well, as you're looking at this left-hand side, it very well could look familiar to you. I hope it does. Here's what I'm getting at. Let's recall a couple of things. We could say, hey, I remember the gradient. The gradient is such an important aspect and idea in calc here. It's the partial derivative of f. It's a vector, isn't it? Partial derivative of function f with respect to y, partial derivative of f with respect to z. You could say, hey, yeah, that's definitely the case. Take a look right up here with r. R is a vector also. Well, what about r prime of t? R prime of t would be dx dt, dy dt, and dz dt. And why am I bringing that up? Well, I hope you're looking at what we just did here, and you can say, now, wait a minute. I see a gradient. This is the x, y, and z components of the gradient right here. You can say, now, wait just a moment. I also see r prime in this mix also. And it only would take a moment. It only would take a moment for you to say, now wait just a minute. This whole left side, therefore, is the gradient of f dot producted with r prime of t. And what you're really saying is the gradient of f and r prime of t have a dot product of 0. Therefore, the gradient of f and r prime of t are orthogonal. They're perpendicular. So here's what we're now going to take a look at. Look at that blue tangent plane. Here's what I want us to take a look at. Wow, you've been looking at derivatives for quite some time. The gradient of f is the vector perpendicular to the tangent plane. We're so used to saying that vector that we could use in the tangent plane equation, we could call it ABC. You know what we could do? We could say the gradient of f could be thought of as ABC. And what did we learn earlier? Well, we learned very nicely that the equation of this tangent plane looked just like so. So I think so very often kids look at this and they'll say, well, yeah, I've done tangent planes so many times. Yeah, what are we getting at? We're seeing that the gradient can represent that A, B, C that we have in front of our other variables. And wow, that's wonderful. It's a derivative with respect to x, with respect to y, and with respect to z, going correspondingly where we'd hope that they would. So I hope that's a very pleasant surprise to you. Maybe you didn't see the gradient being involved in a tangent plane. It most definitely is. Let's take it a step further. The equation of the tangent line, or the tangent plane to the level surface we just saw is right here. You know, it's like your A, B, C. That's where that gradient is going. We just wrote that down. But look, if you have a plane, look in red, that's your gradient right there. That gradient would also help you find the equation of a normal line. So let's just review a little bit. Let's just review just a bit from the previous couple chapters too. We knew that for an equation of a line in 3D, well, we always had x equals x naught plus at. You know what? I'm going to raise that up just a little bit because we're going to have to do a little bit of work here. We'll get to that in a second. And we'll have y is equal to y naught plus bt, and z would equal z naught plus ct. Well, you might remember we could subtract this x naught, we could subtract this y naught, we could subtract this z naught. And remember, the a, b, and c were really the direction vector, the components of the direction vector of our line. So look, we could very quickly see that this is y minus y naught all over a b. This is z minus z naught all over a c. And all of these t's together could be set equal. So if I wanted to get the equation of that normal line, it's the gradient vector is that direction. So the gradient component, 8 components, A, B, C, they're showing up in the equations of the line. We could set the x minus x naught all over A equals y minus y naught all over a B. This is like your A, this is like your B, this is like your C. And that's the symmetric form of your normal line. So right now we're going to close with just finishing up this last example. And of course we have our point x naught, y naught, z naught. And they're asking for us to find the equations of the tangent plane and also the normal line. And what you can do more or less is realize on this left-hand side, that's f. So the derivative of f with respect to x, as we do that, bring down a 2, you get 2x over 4, that's x over 2. Everything else here is just going to be 0 as we're taking this derivative. Let's go ahead and take our derivative with respect to y. We'd get 2y. Our derivative with respect to z is 2z all over 9. And what's your gradient? Well, your gradient is going to be, well, your x component, but plugging in this x naught. So we're going to get a negative 2 over 2. For our y component, we're going to have this, but we're going to plug in our y naught. And then for our z component, well, we've got 2z all over 9, but our z is going to be negative 3. So if we just were to clean this up real quickly, you could see we'd have negative 1, a 2, and a negative 2/3. This 3 cancels down here, doesn't it? This is your A, B, C. So again, we've got our x naught, y naught, z naught. And all we got to do is just write this out real quickly. And you can see we're very close to finishing this up. Here's our tangent plane. We just have to write negative 1 x minus negative 2 plus a 2 times y minus 1 plus a negative 2/3 z minus negative 3 and then just clean it up.